We have already. Yes, yes. Our program. But the idea itself is not. Basically, it's a passion.
I'm just chasing up the information from Jose, so I just need to, so I think some of your delegates wanted to get some of the information for this course.
I submitted a mistake.
Okay, that's fine. If I can find you. Yeah, that's fine, or I'll just try and get it off him and I'll get it to the delegates somehow. Or
If he doesn't have it, I have to.
oh, okay, yeah. Well, that might be just as easy if you've already got it.
Yeah.
And we can email it to them if you like. Because I've got the list of the people attending the course, so
Oh, okay.
we could easily just email it if you like. I've got a USB here too, so we could just do a swap. How's it going?
Oh, yeah.
Need anything else?
It's, yeah, well, you have to ask the students, of course.
Yeah, that's a good point. Tomorrow we'll bring some feedback forms for you too.
Okay.
So,
all right. Oh, you want it on your memory stick now?
yeah, if you,
Okay.
either that or the desktop, and I can save it afterwards. Whatever's
okay.
easier for you.
All right. So what we do is we
Just copy it around the bottom there somewhere. Yeah, that's it.
copy, and then
Just go to that one. Just throw it on the desktop there.
this is you probably.
Actually, just pop it just there. Like if you put it on this, click on the screen. Just right click on the screen there, and then press paste. Perfect.
Yeah. Okay.
And then I'll come and get that in a minute
All right.
after you finish your session.
Don't forget your cruiser.
No, that's right. Great. Perfect.
All right.
Thanks so much. Don't forget.
Yeah. All right, good morning, everyone. So let me first review what we have accomplished yesterday, if anything at all. We defined a linear program that is the maximization of a linear function of n variables. The variables were denoted x1 through xn. The objective function coefficients were a1 through an. And we had a list of constraints, all linear. The constraint coefficients were denoted by little c's. We had organized them in a matrix. The first row of that matrix accommodates the coefficients of the first constraint, etc. And then some linear function of x had to be less than or equal to a bound, and the bounds were denoted by b. And there were m constraints, so the number of variables and the number of constraints don't have to be equal. And well, the condition that characterizes the optimum is the usual condition of tangency between the boundary of the feasible set, the points that fulfill all constraints, and an indifference curve. But there was a kink in that boundary of the feasible set. So the tangency condition translated into the condition that the vector of objective function coefficients is a non-negative combination of the vectors of the constraint coefficients. And the weights in that non-negative combination are the Lagrange multipliers. So one Lagrange multiplier for every constraint. And then the next step was the phenomenon of complementary slackness. A constraint is binding or it is not binding. If a constraint is not binding, it is irrelevant. And irrelevance means that the Lagrange multiplier is 0. Then it doesn't show up at all. And because of this, the product of a Lagrange multiplier and the slack in a constraint is 0. That was the phenomenon of complementary slackness. Some folks of you asked me, why do you speak of slack when you speak of lambda? Well, the Lagrange multipliers are non-negative. For example, lambda 1 is greater than or equal to 0. Okay, and the slack in that constraint happens to be equal to lambda 1 because you have a 0 on the right hand side. So the value of the lambda 1 is the slack. Okay, so if you have slack in your constraint, you have no slack in the condition that the lambda is greater than or equal to 0, and vice versa. That's why it's called complementary slackness. And then using complementary slackness, we have demonstrated the main theorem of linear programming, which states that the solution of the linear program is equal to the value of the bounds where you value them by the Lagrange multipliers. And finally, we have demonstrated that each Lagrange multiplier is equal to a marginal productivity. For example, if you have a labor constraint, then the Lagrange multiplier measures how much more value you get in terms of your objective function if you add one worker to the system. So that is really linear programming in a nutshell. And then now we're going to talk about productivity and efficiency. That is really a nice application of linear programming. So let me see. Let me talk about the difference first. Some of you may have seen this in an earlier presentation of mine. This is a remark by Subhash, who is a big shot in linear programming, and he made the remark recently in a conference on productivity and efficiency in Hyderabad, India. When the American comedian Henny Youngman was asked, "How is your wife?" he responded by the question, "Compared to what?" And this is about efficiency. So efficiency is about the relative performance of something compared to something comparable. For example, your wife relative to a soccer match, or whatever. And so efficiency, which will be measured by benchmarking, measures something relative. Productivity, on the other hand, measures something absolute. I mean, productivity is, how much output can you produce? You don't need to compare. To determine the productivity of an economy, you don't need to compare that economy to another economy. But if you want to know the efficiency, you have to you compare it. So roughly speaking, productivity is output per unit of input, and there is a clear problem if we have multiple inputs. Think of labor and capital, because what is 1 unit of input in that case? You have to aggregate labor and capital. You will need prices or weights, and for those weights it is natural to use the Lagrangian multipliers. They were the weights attached to the constraints, such that the combination of the constraint vectors yields the objective function vector. And the reason that that's a natural candidate is that the Lagrange multiplier measures the marginal productivity. So if you want to know the total productivity, you add up all those marginal productivities. If you have variable returns to scale, as in the U-shaped average cost curve in microeconomics, then you have to make a clear distinction between the marginal cost and the average cost, or the marginal product and the average product. But in linear programming, it's all the same. When you have a linear function, the marginal product is the same as the average product. So you can use those Lagrangian multipliers directly to measure productivity. So let us be a bit more precise. I've done that at the end of yesterday's lecture. We're going to use the main theorem of linear programming, which states that the value of the objective function ax star, where x star is the optimal x, the column vector of variables, and a is a row vector of objective function coefficients, is equal to lambda times B, where B is the column vector of bounds and lambda is the row vector of Lagrange multipliers. So that inner product is equal to lambda 1 B1 plus lambda 2 B2, etc. So we immediately notice that the sensitivity of the value of the objective function with respect to the first bound B1 is equal to lambda 1. Okay, so the Lagrange multipliers are equal to the marginal products. They tell you by how much the value of the objective function goes up as you relax a constraint by 1 unit. This, incidentally, is why they are called Lagrange multipliers, because they demonstrate how a relaxation of a constraint has a multiplier effect on the objective function of the linear program. And they are, in economic terms, productivities. Now, efficiency analysis, so that is about the relative performance. If you want to know how efficient a production unit, be it a firm or an industry or an economy, is, you basically compare its actual output to its potential output. This is a concept that's also used in macroeconomics. So roughly speaking, efficiency is the ratio of actual output to potential output. So the question is, what is potential output? Well, potential output is the maximum output you can produce given your inputs and given the state of technology. And in the theory of benchmarking, which also called data envelopment analysis, something I'm going to explain in great detail, you assume that technology is represented by all the existing techniques. Remember, a technique is a column vector of input coefficients, and as I said yesterday, different firms in one industry can have different techniques, some more capital intensive, other more labor intensive, some more efficient in the sense that they have smaller input coefficients than others. So we're going to determine potential output by looking how much we can produce given the inputs of a production unit and given all the techniques that are around. So if you have an industry and you want to know how efficient or inefficient one firm in the industry is, you do the thought experiment where you relocate the inputs of that firm across all the existing techniques in that industry. Now, why is this technique of linear programming called data envelopment analysis? Well, here is a very simple industry with a single input, say labor, along the horizontal axis, and a single output, say beer, along the vertical axis. And every dot in this graph represents a beer factory. Okay? Now, clearly, you're more efficient if you produce more beer per worker. Okay? So the most efficient firm is the one with the steepest slope. So that is the one in the middle through which I've drawn that straight line. Okay? Because that has the most favorable output-input ratio. Now this is a very simple example because there's only one input and one output. Okay, so now if you want to know, if you take any of the other firms and you want to know potential output, you just take the gap between the observation, which is a dot in this scatter diagram and that straight line. Okay? Because that gap between a point and that straight line, just a vertical connection between a point and that straight line, tells you how much more output a firm could produce if it were to use the technique of that most efficient firm. Okay? So that's how you get potential output. And therefore, the inefficiency of a firm is basically measured by the vertical distance between the point in this scatter diagram representing that firm and that straight line. Okay? And if it's 0, it's fully efficient. This is data envelopment analysis in a nutshell. So all we have to do is to generalize this idea to the case where you have more inputs, more outputs, and and an arbitrary number of firms. In the literature, data envelopment analysis is a chapter of operations research, so it's very closely related to linear programming, and they have their own terminology, and I really had to get used to it. So they speak of decision-making units. So in the previous example, a decision-making unit was simply a firm. It's also called a DMU. And a decision-making unit is a black box that transforms inputs into outputs. So you have an input vector and it produces an output vector. It's quite a general framework, and we will see in a moment that it accommodates input-output analysis. So it encompasses circularity in production. So the notation is the following. The former are the inputs are organized in an input vector x sub I. It's a vector, mind you. xi is not the ith component of x. I should have used a superscript, but when I made this PowerPoint presentation, I hadn't discovered yet the superscript, so I had to do with the subscripts. And an output vector, and as a matter of fact, I hadn't discovered the subscripts either, so I just made the I very small. It's really on the same level. So, the output vector is yi. Okay, the dimensions may be different. If inputs are labor and capital and outputs are very many commodities, then x is the two-dimensional vector and y is a n-dimensional vector. If you include the intermediate inputs, then x would be an n plus 2-dimensional vector and y would be an n-dimensional vector again. So this is just a matter of notation. The notation is very confusing, at least to me, because in input-output analysis, x is used for the gross output and y is used for final demand or the net output. Whereas in data envelopment analysis, x is used for the input and y is used for the output. Okay? So it's a bit different. Here's the connection. If you take a national economy with the gross outputs of the industries organized in vector x, and an input-output coefficients matrix A, and capital coefficients K organized in a row vector, labor coefficients L, also a row vector. Okay, then the output of the economy would be vector X, that is what is delivered by the industries, And the input would, as I said before, an n plus 2 dimensional vector of intermediate inputs, capital inputs, and labor inputs. The intermediate inputs are gross output X, minus AX, and the capital inputs would be KX and LX. Let me think. No, this is too complicated. You may want to take a note here because it's just a bit too complicated. The intermediate inputs. Can anyone tell me what the intermediate inputs are? Yeah. You know, I make mistakes like this because when you make a PowerPoint presentation, you copy paste a lot. But to avoid that you get a repetition of the same sheet every time, you have to make little changes after you have copied and pasted. And then, you know, I forget to make those little changes. Okay. All right. So now we're going to determine for a organization of decision-making units, or an ensemble of decision-making units, how much those units could produce if they would apply the best practice. Okay? And the best practice may vary from decision-making unit to decision-making unit. Because, you know, if you think of an industry with very many firms, then some firms will be labor-intensive, other firms will be capital-intensive. And clearly, to a capital-intensive firm, the best practice is a different leader in the industry than to a labor-intensive firm. Because remember, we're going to compute the potential output given the inputs. Okay, so if you're going to compute the potential output of a capital-intensive firm, you're going to adopt a different technique than for a labor-intensive firm. Okay, so the very concept of a benchmark is a firm of which you want to adopt the technique varies from observation to observation. So the idea is the following. We use the inputs of decision-making unit I, which were organized in input vector X sub I, and we're going to reallocate them across all other firms. And we're going to run the techniques of all the other firms with intensities theta I. So for example, if theta 1 is going to be 0.5, it is as if we're going to mimic the first operation in the industry at a 50% level of activity. Okay? So if you run this scenario, then the total required inputs would be theta I times xi and then summed over I. Okay? So, and this entity will be bound by the available inputs of the firm of which we are going to determine the potential output. Okay? So we take the inputs of a firm, we reallocate the inputs across all the other firms, we run the other firms with intensities theta 1 through theta capital I. If we would do this, making the assumption of constant returns to scale, we would get the hypothetical output of theta I, yi summed over I again. Okay? So that is the whole idea of data envelopment analysis. In the previous example, where we had those dots and that straight line, there would be only one element in this sum. Because in that simple case, where you have one input and one output, there would be only one benchmark. There would be only one firm that's the most productive. So that firm would get the full weight. Okay? And the other weights would be 0. Now here's the linear program that determines the potential output of firm 1. Okay? And clearly, you know, it'll be similar for firm 2, etc. So we're going to run that thought experiment where the firms 1 through capital I are operated at intensity levels theta 1 through theta capital I. The required inputs will be the observed inputs of the other firms multiplied by those intensities. And that can be no more than the available input of firm 1, because we're going to compute how much more firm 1 could produce. Okay? If we're doing this, the hypothetical output would be y1 theta 1 plus y capital I theta capital I. Okay? And we want to produce more. So we take the observed output of firm 1 and we want to expand it by an expansion factor C. So if the variables here are those intensities and that expansion factor C. So if in the solution C is going to be 1.2, our conclusion is that firm 1 could produce 20% more output. Right? If it's going to be 1.25, firm 1 could produce 25% more output. If it could produce 25% more output, it is producing only 4/5 of its potential output, and therefore we say that the efficiency of firm 1 is 80%. Notice that in the solution C equal to 1 is feasible. Okay? Because, you know, you can just let firm 1 reproduce itself by putting theta 1 equal to 1 and all the other intensities equal to 0. Then the first constraint reads x1 times 1 plus 0 is less than or equal to x1, which is fine. The second constraint reads y1 is greater than or equal to y1 times c. So for c we can have 1. So, you know, you can, if you expand output by an expansion factor c, then c is at least equal to 1. So this is called benchmarking. The non-negative thetas in the solution identify the benchmarks of firm 1. So those are the competing firms which firm 1 better takes a close look at. If you were a CEO of firm 1, you would dispatch your managers on an internship at the firms where the intensities are positive, okay? And where the intensities are 0, you can forget about them. Because of constant returns to scale, you could also do input minimization, and it's very simple to see that you get the same solution. Okay, so this is the same linear program as before, but if you divide both constraints by C, and if you make a change of variables, theta 1 over C, you define it as the new intensity theta 1, and you redefine 1 over C as C, then it is very easy to show that everything translates, and what you do is you contract input x1 such that you still produce output y1. Okay, so in the previous example we did output expansion. You could just as well do input contraction. So to produce your output vector, how much less input do you need? Okay, that is equivalent. It is equivalent because of the assumption of constant returns to scale. There are variants to benchmarking where you have, variable returns to scale, and then it's no longer equivalent. Yeah. It's because of constant returns to scale. So we simply assume that, if you observe a technique and you would increase all the inputs by 10%, then the output will go up by 10% as well. If you don't like that assumption, then you're in the ball game of variable returns to scale. And and then it would be nonlinear programming instead of linear programming. But you registered for a course in linear programming, so you would be disappointed. So here is an example. This is an ensemble of 6 decision-making units, and they all produce a single output. Think of beer, but now they use 2 inputs. Could be capital and labor. Anyway, I denote them by x1 and x2. Okay. So this is. But because of constant returns to scale, I can normalize all the decision-making units with respect to output. I can rescale them such that their outputs are equal to 1. And then these are alternative input combinations to produce 1 gallon of beer. Okay? Now, if you look at this scatter diagram, we immediately see that 2 and 4 are inefficient, because 2 and 4 are in the northeast of this scatter diagram. This is input space, so 2 and 4 use relatively much labor and capital, and therefore 2 and 4 will be inefficient. And the question is, how inefficient are they? Well, here in this example, we are going to use the alternative point of view, which is equivalent, namely that of input contraction. Okay? So take firm 2. By how much could we contract its input vector? And the answer is, it's by roughly 15%. You can contract that dot number 2 until you hit the straight line connecting points 1 and 3. Because then you have a weighted average of techniques 1 and 3. What are the weights in that average? Can anyone tell me? Just guess a little bit. If you look at the intersection point of the straight line connecting the origin and dot 2, you contract dot 2 along that straight line, you hit the chord connecting 1 and 3, then you have a weighted average of 1 and 3. And what is the weight of 1 and what is the weight of 3? Yeah, 70% 1 and 30% 3. So the linear program we have just described applied to decision-making unit 2 would yield theta 1 is equal to 0.7, theta 2 is equal to 0, theta 3 is equal to 0.3, theta 4, theta 5, and theta 6 are all 0. And we say that decision-making unit 2, the benchmarks are 1 and 3. So 1 and 3 are the decision-making units where you send your managers to. And, to go out and learn how they do it. Now notice that if you will apply the same technique for decision-making unit 4, then the benchmarks turn out to be 3 and 5. All right, because of constant frequency scale, the capacity to produce output with 3/4 of the inputs, well, that is not very exact, I think. By how much can we contract decision-making unit 2? I claim you can contract it by 25%. But if I look at it, I think it's more like 15%. But, when you type, there is a symbol for 3/4, but there is no symbol for 85/100. So that's why I did it like this. So you can produce it with 3/4 of your input. So it's equivalent. The potential output of firm 2 would be 4/3 of its actual output. Okay. So what is the efficiency of firm 2? Which number do we attach to it? How efficient is firm 2? Yeah, 75% efficient. Yeah, right. Right. So it is it's the solution to the input contraction program, or it is the inverse of the output expansion program. Yeah. This is the only reason why, as we shall see later, if you look at the average efficiency of a constellation, using output expansion, you have to take the harmonic mean. If you would take the input contraction, you can take the ordinary means. Whenever you invert things, you take harmonic means. Okay. Now, let us look at the condition that characterizes the solution to the linear program that determines the efficiency of decision-making unit 1. Okay? In a systematic way, applying the theory we have developed yesterday. So the variables were theta 1 through theta capital I and C. Okay, so we have capital I plus 1 variables. And then we have constraints. Let me flip back. Here it is. And now I'm going to pose you a tricky question. In the first constraint, we have a bound, namely x1. Okay? What is the bound in the second constraint? You have to think of A, B, C. Okay, A is objective function coefficients, B is bounds, C is constraint coefficients. And the format we used was AX is less than or equal to B. And whenever you solve a linear program, you have to write it in that format. So you have to do a little bit of work here. You have to multiply through the second constraint by -1 to get your inequality right. Okay? Okay, so you do that. But what is the bound in the second constraint?
Maintain outputs or increase it.
Pardon?
Maintain or increase output.
Well, the variable is C. That's the expansion factor. Okay, so C applies to Y1. Y1 is the output vector of decision-making unit 1. Pardon? Theta 1? No, theta 1 is not the bound. Theta 1 is a variable. It's 0. Yeah, very good, very good. Because with the second constraint, what you do is first you multiply through by -1 to get it in the format less than or equal to. And then you write it in the format AX is less than or equal to B by placing, and CX is less than or equal to B, CX is less than or equal to B, by placing all your variables on the left-hand side and all your bounds on the right-hand side. But in this inequality, every term has a variable, right? So everything goes to the left-hand side. And there's nothing on the right-hand side. So your bound is 0. Okay? Now let us look at the coefficients in the constraints. In the first constraints, the coefficients are x1 through xi. Okay? Actually, it is a vector inequality, so every component of that inequality is a constraint. Okay? So when I say that the coefficients are x1 through xi, then there are as many components as there are inputs, because for every input we have a constraint. Okay? The bound in the first constraint is x1. And then the coefficients in the second constraint are minus y1 dot 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 minus y sub capital I and plus y1. This is really tricky because first we multiply through by -1 and then we shift it to the left-hand side. Right? So we do two operations. Okay, so the coefficients in the input constraints are x1 through x capital I and 0. And the coefficients in the output constraints are minus y1 through minus y capital I and plus y1, as I just said before. All right. Now, let me see if there's chalk. Yeah. So now we're going to look at the condition that the vector of objective function coefficients, A, is a non-negative combination of the constraint coefficient vectors, which are the rows in C. Okay. Now, A is equal to this vector, because the variables were theta 1 through theta capital I and C. But only C was in the objective function. The other ones didn't appear. Okay, so they have coefficient 0. And then lambda, so this is a vector of Lagrange multipliers, and I suggest you use natural notation. So we have input constraints and we have output constraints, and I'm going to use the notation that row vector W is the vector of input prices. Okay, so that's a common notation in the literature. So W has the same number of components as the number of inputs. And then row vector P will be used for the outputs. Let's see, I'm a bit surprised that I have an inequality there. We have the input constraints and we have the output constraints. Oh, yeah. We have yet another constraint. I overlooked it. We have a third constraint. Can anyone see it? C is non-negative. Remember, I paid attention to that. So, and we're going to denote the Lagrange multiplier of that non-negativity constraint by sigma, just as before. But now sigma is scalar because we have only one non-negativity constraint. Although, do we really need that? Is that constraint binding? No, because C is at least equal to 1, remember? So we can forget about it, I've demonstrated. It's a non-binding constraint. So sorry about that, but we can delete it right away to simplify. So now we're going to look at the constraint matrix. So first we have the input constraints. And then we have the output constraints. So this is the condition. We do have non-negativity constraints, which may be binding. Namely those intensities, right? They may be binding. As in the previous example, I've shown that, there were two benchmarks and the other ones were 0. So we have to add those non-negativity constraints. And this is a good exercise because now you can see how you do it. The variables are theta 1 through theta capital I and C. So if you take the first non-negativity constraint, it's going to be theta 1 is greater than or equal to 0. You have to multiply through by -1 to get it in your standard format. So it's going to be minus theta 1 is less than or equal to 0. Okay? And then the next one will be for theta 2, etc. And the way you do that in general is you just you add the minus the identity matrix. Those are all your non-negativity constraints. And then over here, it's 0 because that was not binding. So now we have our sigma again, but now sigma, what is the dimension of sigma? Pardon? Capital I. Yeah, capital I. That's the right answer. Okay? So this is your first order condition. Okay? And this is how you proceed in general. And now what I'm going to do is to spell it out. Very often in linear programming you're really confused about inequalities, equalities, and whether or not you're allowed to flip things. So in my view, the only way to do it right is to do it systematically. So you write the linear program in the format Cx, the constraints in the format Cx is less than or equal to b, and you write the first order condition in the format A is equal to lambda c. Okay, I always do it like that. So let us look at the first component of this row vector equality. Then on the left hand side we have 0, and on the right hand side we have wx1 minus py1 minus, what do we get? Pardon? Sigma 1, yeah. Okay? Or py1 equals wx1 minus sigma 1. Lagrange multipliers are always non-negative. We have a non-negative combination. So now you can eliminate your sigma 1, and this is something that is done in linear programming. And then you get py1 is less than or equal to wx1. Okay? So your shadow prices are such that all activities break even or are unprofitable. So this is basically why shadow prices are like competitive prices. And now we're going to make a very important observation. We're going to apply the phenomenon of complementary slackness. Remember, there is slack. When there is slack in your primal constraint, there is no slack in your dual constraint. Now we are interested in the benchmarks of firm 1. So we are interested in the i's such that theta I is positive. So we are interested in the techniques with slack in a non-negativity condition. If there is slack in a non-negativity condition, there is no slack in this dual condition. So the benchmarks break even. Okay? And the other activities will be unprofitable. So in that inequality, if done it right, there should be an intermediate step, probably, that the left-hand side, that vector with the zeros and a 1 at the end, is equal to W, and then all the x's and 0, and then P times in that matrix with -1 minus I, minus yi and y1, and also a minus sigma. So I've looked at the first component. The other components are similar. The very last component is something we have to take a look at. The very last component, you have a 1 on the left-hand side. Remember that 1 is the coefficient in the objective function because we were maximizing C, 1 times C. And then if you look at the last component of this, you get that Py1 is equal to 1. Okay? So that is a price normalization constraint. Basically what matters are the relative input and output prices, but the price level doesn't matter. Because all the price system has to do here, it has to identify the benchmarks. They break even and the others incur a loss. But the price level is not important. Another way of putting it is as follows. Instead of maximizing C, we could have just as well maximized 2C, right? Does it make a difference if you use Celsius or Fahrenheit to locate the hottest spot on Earth? Okay? If you would have maximized 2C, then the price normalization constraint would have been Py1 is equal to 2. Okay? So that last component is just a price normalization constraint. All right. So the definition of efficiency, as I've alluded to before, it's going to be the inverse of the expansion factor. 1 divided by C. Now, 1 is equal to Py1. That's the price normalization constraint. I claim that the expansion factor C is going to be equal to Wx1, the value of the inputs. Why is that? This is a deep question. Pardon? We have a bright student in the class. It's the main theorem of linear programming. The value of your objective function, C, is equal to the value of your bounds. And the only bounds we had were x1. We had no bounds on the output side. Okay? So, of the input constraints, the bounds were in column vector x1, and of the output constraints, the bounds were 0, so it doesn't show up. Okay? So you get that the efficiency is the value of output divided by the value of the inputs at the competitive prices, which are the shadow prices of the linear program, or the Lagrange multipliers of the linear program. Lagrange multipliers, shadow prices, perfectly competitive prices, it's all the same. Okay? It is closely related to profit. I mean, profit is revenue minus cost, whereas here we have revenue divided by cost. Okay? But indeed, this is going to be equal to 1 if and only if profit is 0. So you have efficiency if and only if profit is 0. That is because of the constant returns to scale. And it's going to be less than 1. So efficiency is less than a full 100% if and only if profit is negative. Okay? So there is an easy profitability test for efficiency. I've argued before that C is at least equal to 1, and therefore the efficiency is a number between 0 and 1. So it's, it varies from 0 to 100%. Better be, but it's good to confirm it. Let me warn you, the shadow prices which we used are specific to the decision-making unit of which we have evaluated the efficiency. Why is that? Because in the linear program, the bounds were the inputs of that decision-making unit. Okay? So if a decision-making unit has very little capital, for example, then in that linear program, the capital constraint will be a very tight constraint with a low upper bound. And if you have a very tight constraint, then it will pick up a big Lagrange multiplier because it's a bottleneck. So if you would relax that constraint by 1 unit, you would ease the system quite a bit and gain a lot of value of the objective function. Okay? So firms with little capital will have a high shadow price of capital. So we clearly have an aggregation issue of efficiency because the efficiency of decision-making unit 1 is the revenue-cost ratio of decision-making unit 1 at its own shadow prices. Okay, so you have all those efficiencies of all those decision-making units, and if you want to know the mean efficiency of the entire system, you have, it's not easy how to do it. Okay, and there is a literature that because of this there is an aggregation bias, and the aggregation bias clearly has to do with the variability of those Lagrange multipliers across decision-making units. It's getting a bit theoretical, so let me drop that. All right. So now, we're going to make a beginning with productivity. Okay, I hope you're still with me, and if you are, you have learned quite a bit because you have learned how to calculate the efficiency of what is called a decision-making unit. It has, very many applications, not just in economics. There is an application to national economies. I have shown to you how you can, sort of embed the standard input-output model in this framework, but there is a huge literature of this. For some historical reasons, there are some branches of operations analysis which are very popular in the literature. Okay? I don't know why, but it's this kind of analysis is very popular in banking. So the efficiency of banks, and not only to evaluate the efficiency of a bank vis-a-vis another bank, but it's also done quite a bit within banks, because within banks you have you have different offices, and sometimes you want to eliminate some of them because they're inefficient. So then this is applied quite a bit. It is also used extensively in what you might call non-economic sectors of the economy. It sounds a bit funny because in the economy everything is supposed to be economic, but by non-economic sectors of the economy, I mean branches of the economy where prices are not used. Okay, think of publicly run hospitals. I mean, in some countries it's getting more and more organized along, free market lines, but in many countries it is still run along Soviet lines that you just allocate the inputs by negotiations or whatever. All you need for this analysis is inputs and outputs of those hospitals. You don't need prices. The prices are a byproduct of the analysis. They are the shadow prices of the input and the output constraints. Okay? So it's used quite a bit in the health industry as well. Okay? So it's not, they're not free markets, so normally in industries, firms just go bust, and you have sort of a Darwinian selection mechanism. If you don't have it, you can mimic it by this technique. So now let me go to productivity. It's a bit amazing because intuitively productivity is output divided by input. It's more of an absolute measure, and yet we will be able to use the same linear program that is determined that determines efficiency to determine productivity. So there is a nice uniform approach to the two concepts. Now let me, by way of introduction, just as before, do the single input, single output case first. Okay? And we have an input vector x, and it's mapped into an output vector y. Now, if you're interested in productivity as a function of time, in other words, productivity growth, everything depends on time. So the inputs depend on time. In 1 year you have a different input vector than in another year, and the same thing for the output. Now the very relationship between your input and your output may also be a function of time. In other words, your production function may shift through time. And that shift is precisely productivity growth. Okay? So one way to show that would be to index the production function. So you would have f sub t. But another way to do it is to introduce t as a separate argument in your function. And then for every t, you have a special relationship between the input vector x and your output vector y. Okay? Now, in reality, your output may be suboptimal. So if f is the production function, then on the left-hand side, we have the actual output, maybe less, and on the right-hand side, we have potential output. Potential output is simply determined by your production function. In the previous analysis, that production function is determined by the envelope of your scatter diagram. In other words, by the solution of your benchmarking program. Okay? So, the efficiency is denoted by E. So E is simply the ratio of your actual output to potential output. Okay? And technology, or in the single input, single output case, technology is simply given by your input-output coefficient. Okay? And mind you, not the observed input-output coefficient, but the coefficient of input relative to potential output. That determines your technique. There's always a tricky thing in input-output analysis, whether or not to use average input divided by average output. I mean, Leontief's idea was that an input-output matrix represents technology, and if you want to determine technology, it should not be average input divided by average output, but it should be, in a sense, the smallest input-output that is observed, because that determines technology. Okay? So what we get from the last equation is that your productivity, so actual output divided by actual input, is technology, which is potential output divided by input, and then you have to multiply through by that expansion factor, because that expansion factor was output divided by potential output. Okay, so your productivity is like the observed input-output coefficient. Technology is like the best practice input-output coefficient, and you have to multiply through with the efficiency. So if you take the derivative of this expression, you get that productivity growth is technical change plus efficiency change. And indeed, firms may perform better in the sense that they reduce their input-output coefficients either by technical change. This is particularly true for the leaders. The leaders in an industry, if they want to do even better, they have to push out the production possibility frontier. Or if they are followers, firms can perform better and realize productivity growth simply by catching up. For example, by adopting best practices. Okay? Now this is a nice example. It's what I call the standstill example. So I'll look at a firm with input X and output Y. It's constant through time, so nothing changes in the firm, but it may very well be that the production function moves out. Okay, so f of xt of t increases with time. If that is the case, then your output remains the same, but your potential output goes up, and therefore your efficiency is going down. Okay? So your productivity growth is 0, because input remains the same, output remains the same, therefore output per unit of input remains the same, constant productivity. Your efficiency change is negative, the competition is running away, and then if we use the previous result, that productivity growth equals technical change plus efficiency change, it must be that technical change is positive. Okay? So that's a possibility. 0 productivity growth, positive technical change realized by others, and hence negative efficiency change. Now efficiency was defined as the inverse expansion factor, and right. So efficiency change will be minus the growth rate of the expansion factor. Okay, if the expansion factor of our linear program goes up, it basically means that the actual output relative to the observed output is increasing, right? So a greater expansion factor means that the frontier is running away from your firm, okay? So a greater expansion factor means that your efficiency is going down, right? When you solve that linear program, you hope that the expansion factor will be very small, because then you're efficient. So if the expansion factor is going up, your efficiency is going down. So this is just to get you used to a minus sign that will pop up in the subsequent analysis. The analysis will be quite formal, but first let me give you an introduction. We have a linear program, which was the benchmarking program with the variables theta 1 through theta capital I and the expansion factor C. And what are the data we need in that program? Well, we have technology, because basically in that linear program, we are doing the thought experiment where we redistribute our inputs across all the observed techniques. So you have all those input-output combination of the competition, the big input matrix and the big output matrix. They are coefficients in that linear program. Okay? Now, that I call technology. Remember? Because a technique represents one activity of inputs and outputs, and if you stack a number of techniques next to each other, just as in input-output analysis, we have a technology. We also have bounds. There is some overlap because the bounds in that linear program were the inputs. Okay? So that vector of bounds, that is the B vector, and that technology is the C matrix. The objective function was very simple. We just maximized the expansion factor, so that is this. These are the coefficients in the objective function. All 0 and the last one 1. Now we had so technology is denoted by x comma y. So x is the matrix of all input vectors, y is the matrix of all output vectors. If we benchmark firm 1, we pay special attention to firm 1, and firm 1 is represented by the input-output combination x1, y1. Okay? We solve the program C, so the expansion factor C, and the solution of this benchmarking program will depend on all those coefficients, technology x, y, and of course the firm we pay special attention to. Okay? So the solution will depend on the firm we investigate, firm 1 in this example, epsilon 1. So this is a general equation. And now I'm going to differentiate this equation totally with respect to time. So on the left-hand side, I take the derivative of epsilon 1. That will be the efficiency change of decision-making unit 1. On the right-hand side, I have to take the derivative of 1 over c, which is minus 1 divided by c squared, right? Differentiating a simple power function. And then, according to the chain rule, I have to take the derivative of c with respect to its two arguments. Now the first argument of c is the firm itself, and the second argument of c is the technology. Right? Now if you, and then, so you take, according to the chain rule, you take the derivatives of the inputs and the outputs of firm 1 with respect You differentiate c with respect to x1 and y1. Now x1, remember, x1 were the bounds in that benchmarking program. Because in that benchmarking program, you try to produce as much as you can given the inputs of firm 1. They were the bounds. Now c is the solution to the linear program. When you differentiate the solution of a linear program with respect to a bound, what do you get? What is the sensitivity of your solution of a linear program with respect to a bound? It's the shadow price, right. And then finally, the last step is you have to multiply through, again, according to the chain rule, you have to take the derivative of x1 with respect to time. Okay, so what you get is a shadow price times the derivative in that input. And you get the same thing on the output. So what you get the changes of the inputs valued by the input prices. And you get the changes in the outputs valued by the output prices. So what you get is the solo residual. You get the change in the growth of your output minus the growth of your inputs. So that is the first part of total differentiation. That will yield the solo residual. And now we also have to take the derivative with respect to the environment. Now if you take the partial derivative with respect to the environment, fixing your firm, if the environment is changing, if your expansion factor is changing, even though the firm itself stays put, it means that the frontier is moving out. It means that you're becoming less efficient. Right? I mean, but that will be due to technical change. Nothing happens. Okay, that is because the environment, the change in the environment measures the production possibilities. So that will yield the technical change. So here is the more formal analysis of what I've just done. We begin with the same reduced form of the benchmarking program. So C is the solution of benchmarking firm 1 on the entire industry. And we take the inverse to get the efficiency of firm 1. And I take, on the left-hand side, I take relative derivatives or elasticities if you want to. So on the left-hand side I get efficiency change as a growth rate. It's a derivative of epsilon 1 divided by epsilon 1 itself. On the right-hand side I get the derivative of 1 over c, which is minus 1 over c squared. And then times dc dt according to the chain rule, and then divided by the right-hand side to make it a percentage. So I divide by 1 over c, that is equivalent to multiplying by c. And then I simplify this, I get minus dc dt over c. And then I evaluate dc dt as I've just argued before. So I take the partial with respect to x1, chain rule, derivative of x1. I take the partial with respect to y1, chain rule, derivative of y1, and I take the partial of c with respect to the environment, xy. Okay? Then, as you have noted, the sensitivity of c with respect to x1 is given by the Lagrange multipliers. So it's the input price, is w. And you have the same thing over here. It is going to be minus p, because you had those minus ones in the constraints of the outputs. And then finally we have dc, the sensitivity of the expansion factor with respect to the environment. So we get that the efficiency change is here we have this should simply not be there. So we get that the efficiency change is the change in the value of the outputs of firm 1 minus the change in the values of the inputs. Or, no, sorry. I divide through by C. Oh, yeah, sorry. It should have been there. I divide through by C. It was correct. I divide through by C. So dc dt dividing through by C, I get the efficiency change as a percentage. Here this C now drops out. And here I get W dx1 dt over C. And here I get the change in the expansion factor due to change in the environment. Then I divide through by py1, that's equal to 1 because of the normalization constraint, so that's allowed. And C is equal to Wx1 because of the main theorem of linear programming. So I get the change in the outputs where I use the value shares of the inputs using the prices minus of the outputs using the output prices, and I get the change in the input. So this green expression is precisely the solar residual, and this is minus technical change. So I get that efficiency change equals the solar residual minus the technical change. And then it's customary to rearrange terms, so you get that the solar residual, which is the measure for productivity growth, because productivity is output divided by input. So productivity growth will be output growth minus input growth, right? So productivity growth, the green expression, will be efficiency change plus technical change. And that again states in a precise manner what I said before, that firms may progress either by pushing out the production possibility frontier or by catching up. Okay, this is what I just said. The solar residual, the measure for productivity growth, equals efficiency change plus technical change. Now, neoclassical economists, including Solow himself, identify the solar residual. The solar residual, by the way, is the measure for total factor productivity growth with technical change. Neoclassical economists believe that productivity growth is due to technical change. Why? Because neoclassical economists assume that the economy is perfectly competitive and that everything is efficient. And then indeed the only way to make progress is by technical change. Okay? In many input-output studies, however, we don't make that assumption because the real world out there, which is hardly visible because the windows are not clean, there need be no competition, and then productivity growth may be achieved just by catching up, technical change. So neoclassical economists just miss out on that term. So empirically, not surprisingly, the first source of growth, the first I mentioned here, the blue, let me call it the blue term of growth, technical change is important to advanced economies. Those are the ones close to the frontier and therefore the ones moving out the frontier. Whereas efficiency change is very relevant to developing economies. I've been invited to lecture in South Africa. South Africa is quite an advanced developing country, but it is a developing country. Okay, and in the Western world, in academics, we are all working on technical change that's very hot now. Patents, innovations, things like that. A very important source of productivity growth. So they asked me, what kind of research should we be doing to be hot? So I said, slow down, catch up, right? And catch up not by doing that type of research, but just, make sure that the South African economy adopts best practices. There's much more scope to be made there than by pushing out the frontier. All right. Thank you. Oh, today's lecture, this is a very new book. So if you found it too quick, because we did a lot of work, and if you want to read it at your leisure, a brand new book came out. It's called The Economics of Benchmarking. So it's all about that linear program with very many business applications. Okay, and according to my colleague Hal Varian, the microeconomist at Berkeley, anyone interested in performance evaluation will want to read this book. So, wow. Yeah. So that's a good reference just for today's lecture. So thank you for your attention, and tomorrow we're going to apply all this to computable general equilibrium models.
Excuse me. Don't forget it.
Oh yeah. Good point. You don't want to register what I'm saying during coffee time. Yeah.
So this is the girl who was speaking before. She sent my email for me tomorrow in the last session. Okay?
I want just this presentation.
Yeah, but that
The
was
day
tomorrow.
one and the day two.
And the day two?
I mean, yesterday,
Yes,
linear
good.
programming, and today, linear.
And tomorrow is the last one.
Oh, for the last.
Yes.